We'll now discuss some very basic approaches for integration. So first we have a list of formulas. So the integral of a constant is just that constant times x. So for example, the integral of 5 would be 5x. The integral of x to a power, well, we add 1 to the exponent and then divide by that number, provided the exponent's not negative 1. In that case, we would be dividing by 0. The integral of cosine ax is 1 over a times sine of ax. And the integral of sine of ax dx is negative 1 over a cosine ax plus c. The integral of secant squared ax is 1 over a tangent ax. The integral of cosecant squared is negative 1 over a cotangent ax. The integral of secant ax tangent ax is 1 over a secant ax. And the integral of cosecant ax cotangent ax is negative 1 over a cosecant ax. The integral of e to the ax is 1 over a e to the ax plus c. And the integral of 1 over x dx is the natural log of the absolute value of x. Anything of the form integral of 1 over the square root of a squared minus x squared dx is sine inverse of x over a plus c. The integral of 1 over a squared plus x squared is 1 over a tangent inverse x over a plus c. And finally, the integral of 1 over x times x squared minus a squared dx is 1 over a secant inverse of the absolute value of x over a plus c. So these are our very basic integrals. So our goal is to make other integrals look like one of these. We'll start with just a very basic substitution. We seem to have an extra dx here. This should just be a 1. So in this case, I'm going to let u be equal to 8 plus 2x. So du would be 2dx. Since I don't seem to have a 2dx here, I'll divide both sides by 2 to get 1/2 du is equal to dx. So this now becomes 1/2 times the integral of 1 over u du. So 1/2 ln of the absolute value of u plus c, which is 1/2 ln of the absolute value of 8 plus 2x plus c. So in general, we want to use substitution when we see a function and its derivative. If we see something that is a little complicated that has an x, we can use a very basic substitution. If you see an x squared, you're also looking for an x. If you see an x cubed, you're looking for an x squared, etc. If we have a single term on the denominator, like we do here, we can split these fractions. This is the same thing as the integral of x cubed over the square root of x, plus the integral of x to the 4th over the square root of x. And then we can simplify these. So this is 3 minus 1/2 is 5 over 2. 4 minus 1/2 is 7 over 2. So I'm going to add 1 to the exponent and then divide by that number. And the same thing for the second term. Add 1 to the exponent and then divide by that number. And so we have our integral. If the degree on the top is bigger, like it is here, I can divide my fractions, or divide my functions. So x minus 2 goes into x squared plus 3x minus 8. So I need to know x times what is x squared? Well, x times x. Multiplying down, x times x is x squared, and x times negative 2 is negative 2x. And I need to subtract this, so I'll change the sign all the way through. These terms cancel, and I get 5x. Bring down the next term. X times what is 5x? Well, x times 5. 5 times x is 5x. And 5 times negative 2 is negative 10. And I need to subtract this, so I'll change the sign all the way through. And I get 2. So this is the same thing as the integral of x plus 5 plus 2 over x plus 5 dx. The integral of x is 1/2 x squared, and the integral of 5 is 5x. This term here is a little more complicated. So I'm going to let u be equal to the denominator. So then I have that du is just equal to dx. This gives me 1/2 x squared plus 5x plus 2 times the integral of 1 over u du. So 1/2 x squared plus 5x plus 2 times ln of u, which was x plus 5, plus c.